Okay, so lesson 2, electricity moving. Last lesson we looked at static electricity. So we were looking at rubbing a cloth, and we were looking at the fact that the rod could then pick up some paper, and we said it's to do with these electrons inside the atoms moving from one to the other. Well, this one we're going to use a different way to make electrons move, and the way that we're going to use to make it move this time is we're going to use a chemical. So this is a cell. So in here you've got a positive chemical and a negative chemical, and the electrons want to flow from one end to the other. But what you're going to do is you're going to make it hard for the electrons to flow to each other, because the thing you've got to remember about charge, it's one of the key things to do with charge, and that's the opposites attract. Okay, opposites attract. A bit like a north pole and a south pole of a magnet attract. Well, opposite charges attract. Positive charges attract negative charges. That's why this electron doesn't go zipping off into space, because it wants to stay near this positive proton, because it's like a north pole of a magnet to the south pole of a magnet. Okay, so on my cell, this is the positive end of my cell, so the positive part of the battery, you know, the sticky out bit. And if you imagine, you can snap that big line in two and turn it into a cross. So that's how I remember it. Whereas you can't snap that one in two, it's already in two. So this one is the positive part of the cell. Now, and this part is the negative part of the cell. But you don't make it easy for the electrons. You make them go around a circuit. So the electrons will go, remember, opposites attract. So the electrons will want to go to the positive part of the battery. So they want to get there. But you don't, that's why there's a gap there. Otherwise it would be short circuited and it would just go, okay, I'll actually take the easy route, I'll just go there. But you don't let it do that, because you leave a gap. So it's got to go all the way around the circuit to get here. It says, I hate being with other electrons, because if it's got the same charge it repels, but I love being near positive, so it goes all the way around the circuit to get to the positive. Okay, that's the first thing you need to know. Now, secondly, this is a cell, because there's only one bit of positive and one bit of negative. But if you want a battery, what you do is you make sure that you line up lots and lots of cells, and that now creates a battery. And so if each one of these cells was 3 volts, then that is a 9-volt battery. Okay, they're the square ones. So remember I said it's going to be about electricity moving? Well, I know that my electrons are going round the circuit and they're taking their charge with them, okay? And the voltage is how much energy you are giving each bit of charge. Okay, and then when they go around the circuit, they've got to use that energy up. So let's have a look at a circuit that's a little more interesting. So let's put in a light bulb into my circuit. Okay, so I've now got a light bulb in my circuit, 9-volt light bulb. 9-volt circuit, I've got a light bulb. And here's the thing about circuits. If I was to measure how much energy each bit of charge has here, so how much energy does an electron have there, I need to put in a voltmeter. And what the voltmeter does is it goes, okay, how much energy per unit charge here, how much energy per unit charge here, what's the difference? Now the key thing is, if in a circuit, electrons always run out of energy by the time they get back. It's like they've paced themselves in a marathon and they only just got enough energy to cross over the finishing line. They only just make it back. So it starts off with a full amount of energy, which was 9 volts, and it ends up with 0 volts because it doesn't have any work left to do once it's got past this light bulb. So I know that this voltmeter is going to read 9 volts. And what that's telling me is that there is a difference in the amount of energy per unit charge between here and here of 9 volts. And that's why we have to put this voltmeter in parallel. So these two lines are parallel to each other. That's what those dashes mean. Parallel, all a parallel line is two lines that will never ever meet. And that's the symbol for it. And this is one of your spelling test words. Remember how I said you could remember how to spell parallel? You can remember how to spell parallel. Because it's one R, but the double lines make the double L, so parallel. Okay, so the voltmeter must be put in parallel. Let's make it a slightly more interesting circuit. This circuit's really boring still. Okay, so I'm going to go for another 9 volt circuit, but I think you've got the hang of adding cells together to get the total voltage, so I'm just going to put 9 volt cell. But this time I'm going to have 3 light bulbs, and they're all got the same resistance, so they're all as difficult as each other for the electricity to get through. And if I put a voltmeter here across one of them, let's see what that will be. And if I put a voltmeter here across 2 of them, you can see what that's going to be. Then I put a voltmeter across here, across all 3 of them, and I can see what that one's going to be. So I call that one the voltmeter 1, voltmeter 2, and voltmeter 3. So V1, well, this light bulb gets 1/3 of that 9 volts, and this one gets 1/3, and this one gets 1/3. So V1 measures how hard it is for it to get across just one light bulb. So 1/3 of 9 is 3 volts. Voltmeter 2 is measuring how hard it is to get across 2 light bulbs. So if it takes 3 volts to get across one light bulb, I know it's going to take 6 volts to get across 2 light bulbs. And equally, I know it's going to take the full 9 volts, because that's the total energy at the start and that's the total energy at the end, which was this one here, because it's got nothing else left to do by the time it gets back to here. So we're all good there. And if you notice that each light bulb has now got a voltmeter reading of 3 volts, whereas before on this one, where it was just one light bulb on its own, that one had a reading of 9 volts. And remember, we said that voltage is how much energy each bit of charge has. So that means that there's less energy available for each light bulb, because they've got to share it out amongst themselves. Okay? And one last bit, and that's to do with current. So current is the rate of flow of charge. And basically what that means is, it means how fast do the electrons go around the circuit and how many have you got going around. Okay, rate of flow of charge. So it's a bit like a river. How much water do you have in the river? How fast is the river moving? Okay, they're the 2 things that give you current in a river. How fast are the electrons moving, and how many are moving? That's what gives you the current in an electric circuit. And you measure the current in a circuit using something called an ammeter. Okay, and this has to be in the circuit. This has to be in the circuit. And the reason why that has to be in the circuit is because it's measuring how much water is going through that pipe there. It's measuring how much electricity is going through that pipe. So it has to be in the circuit. And when you've got one component followed by the next component, followed by the next component, followed by the next component, this is a special kind of circuit. We call this circuit a series circuit. And if you think of TV series, where that would be episode 1, 2, 3, 4, and then back, okay? Each episode follows the next one. Okay, follows the last one, sorry. And it wouldn't matter where you put your ammeter in this circuit, it would still read the same amount. You could put your ammeter anywhere, and you could put as many ammeters as you want in. It won't make any difference, because what you're measuring is, if you look, you pour the electricity in there, and then it's got to get around the circuit. It's got no choices. This circuit doesn't have any choices. It's a series circuit. The voltmeter doesn't count as a choice because it's way too hard for the electricity to bother going up here and then back down there. This is just there to measure the voltage, okay? It's way too difficult for the electricity to bother going this way. So it doesn't have any choice. So what you started with is what you end up with. It's like a hose pipe. The amount of water that you put in the start, as long as you don't have any leaks, is the same as what you have at the end. Okay, next lesson we will move on to parallel.